So like I said, the first thing we want to do is calculate the time constants that are involved for this problem. Okay, so first let's look at internal equilibrium. Okay, so internal equilibrium, right? This is our tau diffuse time constant. So for this problem, we would say, let's use this relationship, delta t is equal to 2 times alpha, or 2 times the square root of alpha times time. Okay, so solving that out for this problem, we have our tau internal or tau diffuse. You'll see this both as tau diffuse and tau internal, by the way, is equal to L. So here we have L squared divided by 4 times alpha. Okay, so I think we're given K, rho, and C in this. If you do the calculation, it ends up being 700 seconds. Okay, so what is that saying? That is saying that when I turn off that electricity, the center line there, right, where the condition is kind of changing at the boundary, and we're losing generation, but the center line is not going to see that change in the external condition for about 700 seconds. Okay, so it takes that amount of time for the heat to kind of diffuse in, or the cool to diffuse in, right? Okay, so that's the diffusive time constant, and then external equilibrium. External equilibrium, we'll say tau LC is equal to our surroundings times C object. Okay, if you do that, here we have tau LC is equal to the surroundings resistance is 1 over H bar S times A. Let's see, what is this? Tau should be AS. Times what's the specific heat or the object, or the heat capacity of the object? It's going to be the volume, which is AC times L times rho times C. Okay, so we actually end up with assuming that AS and AC are the same for this. Let's see, actually, how does that work? Might be a mistake in here. Anyways, with the calculation, my notes is as follows. So it goes L times rho times C over H bar S. Tau C. Just make sure that. Yeah, which doesn't. So this should be volume, right? And that's different from. So okay, there's this. This actually should remain like this. It should remain AC over AS, I think. AC times L. The volume, it shouldn't change like that. So I'll have to go back. I mean, ultimately it scales things a little bit, but the point of this exercise, and actually this isn't especially the specific calculation, while I want to do it right, isn't the point of what I'm trying to say here. So I'll just give you the tau LC is equal to 5,600 seconds. Okay, so let's say we did the calculation correctly. Okay, and we came up with an answer where tau LC is 5,600. Right, the point of what I'm saying here is, let's look at these two things in comparison to each other. Right, tau LC is 5,600. Tau diff is 700. Okay, what does that say? That says that it's going to take much less time for the heat to propagate in and sort of come to an internal equilibrium than it is for this entire body to come to equilibrium with its surroundings. So we can use this information and we can kind of predict the behavior of this particular problem without actually doing many more calculations. Right, so how would we do that? So let's actually sketch out here. So on the left-hand plot, let's take temperature here, T as a function of position. Or, sorry, this is position R. All right, so temperature is a function of position. And let's plot temperature at different times. So at the first time, let's say time equals 0. Right? So at time equals 0, let's plot our kind of steady state solution before this anything really happens. Okay, so that would look something like this. Right? You have at the boundary here, we have an adiabatic condition, so that's a slope of 0. On the right-hand side, we have convection occurring. So this would be, let's say over here, this is T, what do we call that? T infinity. So T infinity down here. So we have a gap between our wall temperature, our surface temperature, and the surroundings temperature. So that's at time equals 0. Okay, so what we just decided is that it's going to take much less time to come to internal equilibrium than it is to come to external equilibrium. So what's the plot gonna look like at, say, 700 seconds? Right? At 700 seconds, I'm saying that the wave has sort of propagated through, and we're at our first kind of hint of internal equilibrium. So what would that look like? Well, that would be something like this. Oops, I don't want it straight. Be something like this. Okay. So why did I draw it up here and not down here, right? Because it's taking a while for it to actually come to equilibrium with the surroundings. Internally, it's equilibrating much faster. So right away, you see at 700 seconds, you start to see it equilibrate. Okay, and then if we look at this as a function of time, then for other times, maybe at tau LC, let's say 5,600 seconds, now we're starting to see that the whole body is coming into equilibrium with the surroundings down here. It's a really bad line. So this would be at T equals 5,600. And then as we go to infinity, right, this is going to approach T infinity. Okay, that make sense? All right, so we've done that for temperature as a function of position. We could also do kind of the same plotting exercise for temperature as a function of time. So let's do that real quick. So if we look at our initial condition, right, we have, let's see, over here, we have a temperature at the inner wall that's pretty high, and we have a temperature at the outer wall that's pretty low. Okay, so if we were to plot those two things as a function of time, let's say the temperature at each of those two conditions is a function of time, how would that look? Well, let's start with the inner symmetry point temperature. So that's going to be up here, same temperature as the other one. That one, as a function of time, you're going to see it drop pretty quickly, right? It's going to drop to come to equilibrium with the rest of the body. Right? And then very slowly over time, then the entire thing is going to come down and drop down towards the ambient temperature condition. And so this is at R equals 0. So what's it going to look like at the outer wall? Draw that in green. So at the outer wall, we started off down here, right? At the outer wall, we actually are going to see that temperature go up. Okay, and it goes up like this. And eventually it's going to come to equilibrium with the inner wall condition, and then the whole thing's going to come down together. All right, so this one would just kind of trace along with the other one. This is at R equals, oh, I used X, didn't I? Well, okay. R out, we'll call it. Whatever. Okay, X equals L. A little careless today. All right, so, but you get the idea, right? Inner wall and outer wall, or inner symmetry point and outer wall, and it sort of comes to equilibrium with itself. Okay. So that's kind of two different ways of thinking about that. So I think that probably makes enough sense. We have this tool now that we can use to kind of characterize the problems. So I have another slide here. Let's skip this for the sake of time.